In this physics question, we are covering two main subsections of mechanics, and those are energy conservation, as well as explaining Newton's laws. So we have a spacecraft entering the atmosphere of Mars must decelerate to land undamaged on the surface. Figure 1 shows a spacecraft of total mass 610 kilograms, entering the atmosphere at a speed of 5.5 kilometers per second. And then we're trying to calculate the kinetic energy of the spacecraft as it enters the atmosphere. We want to give our answer to an appropriate number of significant figures. So to give our answer to an appropriate number of significant figures, we have to look at the numbers that we have. We have 5.5 as well as 610. The 5.5 is given to 2 sig figs. The 610 is given to either 2 or 3 sig figs, we can't tell. For our final answer, we have to give it to the same number of sig figs as the lowest number of sig figs in our question, which in this case is 2. Kinetic energy is half mv squared. That's a half times 610 multiplied by v squared, which would be 5.5 10 to the 3 all squared. And that to 2 sig figs is 9.2 times 10 to the 9 joules. For 2.2, a parachute opens during the spacecraft's descent through the atmosphere. Figure 2 shows a parachute spacecraft system with the open parachute displacing the atmospheric gas. This causes the system, as you can imagine, to decelerate. And then we're given the direction of travel, we're given the displacement of gas, the direction of that. Explain with reference to Newton's laws of motion why displacing the atmospheric gas causes a force on the system and why this force causes the system to decelerate. The momentum of the gas is changing. The gas to begin with is stationary on average. As the parachute passes through it, the gas now moves in this direction and in this direction. It now has gained some momentum. From Newton's second law, force is proportional to rate of change of momentum, and we can just write that as equals to because the proportionality constant is just 1. So force is equal to rate of change of momentum. If the gas is experiencing a change in momentum, it must therefore be experiencing a force. That's Newton's second law. And from Newton's third law, we can then say that if the gas is experiencing a force, and that's from the parachute, then the gas must be exerting an equal and opposite force on the parachute. That force will be in the opposite direction to motion. So this will be the drag force that we receive from the air on the parachute. That causes there to be a resultant force on the spacecraft, which causes it to decelerate. And that deceleration will be in the same direction as the resultant force, which will be a combination of the drag force as well as weight. Okay, so for 2.3, it says, as the parachute spacecraft system decelerates, it falls through a vertical distance of 49 meters and loses this much kinetic energy. We also have 3.3 times 10 to the 5 joules of energy transferred from the system to the atmosphere. We're given the mass of the system, and then we're trying to work out the acceleration due to gravity as it falls. So just bear in mind for this question, we're trying to work out the acceleration due to gravity, which is g. We're not trying to work out the deceleration of the system. We're on a different planet here, so the acceleration due to gravity is not just simply 9.81. The deceleration of the system we could work out because we know what the initial speed is. We can work out the final speed from this, and we have a distance. We can work out what deceleration is from those quantities, but that's not what we're interested in. We're interested in working out what the acceleration due to gravity is. Now, the fact that we're given various different types of energies suggests to me that we're going to be considering energy conservation in this question. If that were the case, we would have to use mgh for gravitational potential energy, And I'm assuming we're going to be then rearranging that equation to work out what the acceleration due to gravity is. Okay, so first let's think about the different stores of energy that we have. So there's kinetic energy. We're losing some kinetic energy. There's also gravitational potential energy, which will be lost as the parachute spacecraft system falls. And there's also the energy of the air molecules. So this much energy is transferred from the system to the atmosphere. In other words, transferred to the kinetic energy of air molecules. So we have three forms of energy. We have KE, we have GPE, and then we have the KE of the air molecules, which I'll just call KE-A. KE of the parachute spacecraft system, I'll just call S for spacecraft. Okay, so we need to set up an energy conservation equation. So what we could do is, we can add up all of the changes of these individual stores of energies, and all of those changes should sum up to make 0. So what I mean by that is the change in the kinetic energy of the spacecraft plus the change in GPE of the spacecraft plus the change in the kinetic energy of the air molecules, as these are all of the three different forms of energy that are being transferred between one another, this whole sum should be 0. As if we were to have, let's say, one store gains energy, then that means one of the other stores or both of the other stores must lose an equivalent amount of energy. If we have a loss of energy in a particular store, we make that negative. If we have a gain of energy in a particular store, we make that positive. So, the spacecraft loses minus this much kinetic energy. We also lose an amount of GPE which corresponds to the mass, 610, times G, so mgh, times the height. And the air molecules are gaining energy, so plus 3.3 times 10 to the 5. So what this equation is telling us is that the loss of kinetic energy of the spacecraft and the loss of gravitational potential energy of the spacecraft, those two energy forms will go to the kinetic energy of the air molecules. So we can now rearrange this equation for G. So minus 2.2 10 to the 5 plus 3.3 10 to the 5 is 610 times G times 49. Rearrange this for G. Left hand side, this bit here is 1.1 times 10 to the 5. Divide that by the 610 times the 49. And this gives us 3.68, or about 3.7 meters per second squared. 2.4. Dust from the surface of Mars can enter the atmosphere. This increases the density of the atmosphere significantly. Deduce how an increase in dust content will affect the deceleration of the system. Okay, so if we think of, we want to consider how the deceleration changes. Deceleration is related to force, and force is equal to rate of change of momentum. Momentum is mass times velocity. So if we are to increase the density of the atmosphere, we will increase the mass of the air that is displaced, and therefore we will increase the change in momentum of the air, and therefore we will increase the force, and if we increase the force, we will then increase the deceleration.